Hello class, today we are going to be working on traffic signals again, and today we're getting to the nuts and bolts of how to time a traffic signal, how to calculate how much green time each movement gets. And if you remember right, each movement we call a phase through there. And it could be a number of movements at once. It could be if all the cars from one side are going at the same time, both left turns and through movements could be all in the same phase, and we'll see that a little bit again today through there. This is where we left off last time. We had capacity, which was equal to the saturated flow rate times the effective green time divided by the cycle length of the signal. And that's the capacity for one movement. That's the capacity for a lane group or a movement through there. So if we were looking at the southbound through movements, that would be the saturated flow rate for the southbound through lane or lanes times the effective green time of the southbound through movement divided by the cycle length of the signal. And the cycle length is universal. Everybody, all phases are on the signal are running at the same cycle length through there. How to figure out how much green time that we need for a movement for one phase at a traffic signal is based off of which lane group within that phase has the most critical flow. And we define that critical flow by it's the closest to capacity. And we call that over a volume to capacity ratio, or in the critical lane group, we call it the flow ratio of V over S of the phases right, through there. And so we may have, for each phase, we may have more than one movement. So we phase 2, if we just had a 4-phase signal, phase 2 may be both left turns, a permissive left turn and a through movement through there. We have to look at the left turn separately and decide if that's closer to critical flow or if the through movement is closer to critical flow. All right, and so it's based on the capacity of that. And so we come up with, then we look at, we go through the signal and we look at the critical lane group, and we're going to do an example here in a second. I'll make it a lot easier to look at. But we look at these critical lane groups for each phase, and then we sum those together, and that's that capital Y sub C. That's this guy right here. And that's the sum of the flow ratios for the critical lane groups from all the phases. And so we say 1 through n is the number of critical lane groups, but that's also the number of phases you have, right? So each phase has a critical lane group. We take that critical lane group out of each phase, calculate this ratio, right, the flow ratio for that, and we sum those together, and that gives us this Y sub C. And it'll, like I say, this will make it easier. Maybe this will make it easier to look at. All right, so we've got this example. We have an intersection that has a 3-phase signal, right? So there's only 3 phases. We've got them numbered down here: phase 1, phase 2, and phase 3. On phase 1, northbound left and southbound left are moving at the same time. So they're sharing a phase on the traffic signal. Phase 2, the northbound through and right and the southbound through right movements are going at the same time. So they're sharing a phase. All right, and then phase 3, the eastbound left and westbound left and eastbound through right and westbound through right, they're all going at the same time. But these have their own lanes, and so that's the difference. So you can see these have their lanes split out. All right, so basically 3 must be the minor road, is running the minor road on the east and west there, and the left turns are going the same times as the through, so that means it's all permissive. Right? There's no arrows here for the left turns. Phase 1 is split out. These have arrows. You'll get a protected left turn movement here on phase 1 through that, and then you get phase 2 is the green ball indication for the throughs on the north and south. So that must be the major phase through here. And you can see that by the numbers here. You can see this is the flows, right? So here's the analysis flow rate. Here's the saturation flow rate. Analysis flow rate, saturation flow rate for the southbound left, for the northbound left. They didn't line these tables up very well. For the northbound through right, this is the analysis flow rate. This is how many cars you expect to have, right, on there. Here's the saturation flow rate. This is how many you expect, 1,125. You could have, the saturated flow rate is 3,400, right? And so this V over S is this ratio. It's the analysis flow rate, the volume you think you have, could be measured or it could be predicted, over what your saturation flow rate is, right? S is your saturated flow rate, V is the flow you've got. Right. So our V over S for this first one is 330 divided by 1700. That's our V over S for that. And so what's our critical lane group, right? So what we're supposed to be adding together are the critical lane groups, CI, the critical lane groups for that. And the way we figure out what the critical lane group is which one has the highest ratio. And that's literally what we're checking. So if I get my calculator out here, we take 330 divided by 1700, right? Oops, I typed something wrong. Divided by 1700. Now I get 0.19 here, and somewhere I've got a pen. I'm really bad at writing on here. So this would be, whoops, 0.19, right, for that lane. And let's look at the southbound left. We've got 365 divided by 1750, right? And that is going to be, oops, I should have put point. Actually it's 0.21 through there. I'm not good enough with this pen yet, so let's start over. All right, so this lane group, it's V over S. That was, come on pen, don't be mean to me. All right, we get 0.19, and this one is 0.21, right? So which one's the critical lane, right? It's going to be southbound left. And that is going to be your critical lane group V over S ratio for this phase, for phase 1, right? And we could go through and we could calculate now what's the 1125 divided by 3400, right? That's 0.33. Right. And then we've got 1075 divided by 3300, and that's also 0.33. So I'm rounding things right to 2 decimal places. I guess you could use more decimal places, but we don't normally. And over here we've got 0.17. And 80 divided by 600, 0.13. And we've got 250 divided by 1750, 0.14. And then we had 285. And this is very riveting video, isn't it? Me doing math. 285 divided by 1800, I get 0.16 for that. Hey, I'm actually writing better as we go. It's good practice for me with this writing tab. All right, so here's our V over S ratios for each lane. For each movement we've got out there. And now we have to pick the critical one for each phase. And so this one, these are equal. So sure, we're going to pick 0.33, which is our critical movement over here. Which lane is closest to capacity? This guy, right? And so now our Y sub C would be equating our 0.21 plus 0.33 plus 0.17, right? There we go. And whatever that equals, I guess I'm going this far, I might as well calculate that. 0.21 plus 0.33 plus 0.17, right? 0.71 is what I get. Come on, pen, where'd you go? There we go. I spoke too soon about writing better. There we go. So 0.71 is our Y sub C, right? So if we went back to here, that's what this guy is. So I have taken the volume to saturation rate ratio, which is an indicator of how close to capacity this lane is, a single movement is. We add up the critical one, which is the highest one for each phase, and add those all together. It gives us this y sub c. So that's that sum of the flow ratios for the critical lane groups. Southbound left is a critical lane group. Southbound through, actually, you can take your choice here. They're both the same. Is a critical lane group. Eastbound left is a critical lane group on phase 3. All right. So we're picking the worst lane of each one, the one that's busiest through there, and that's what we're adding together to get that y sub c. Right, through that. All right, so that's that first piece. And then, once we know that, right, so once the idea there is just what's the flow ratios for that critical lane group, you're going to see how we use this here in a second through there. So it may seem weird just to calculate that because we want to, but we did. We're going to use it in a minute here, and then you'll see why we care about it. And now we want to know what our minimum cycle length is. This is one of the biggest deals of traffic signal timing, is figuring out how long the cycle should be, which is, again, if you get a green light on southbound through, how long does it take for that green light to start again on southbound through? And we say it's 60, 80 seconds. We try to keep it fairly short because we don't want people to wait too long. But really, NDOT signals out on state highways tend to run, they're usually 90 to 150 seconds. They don't have any that are 60 that I've ever seen before. Some local agencies do. Typically, higher flow intersections, you're not going to get below 80. That's about the minimum you're going to get, because you have to have enough time to serve all of the cars that are waiting. That's the goal, right, through there. And some signals you can't. You just don't have enough lanes to get people moving through. Then you're over capacity, and it's a whole other problem. Right through there. And so the way we calculate this minimum cycling is we're going to use that sum of those critical lane groups. And so here's this equation for C minimum. So this is our minimum cycling. You can have a larger cycle length if you want. In fact, we usually round up, and I'm gonna say we round up to 1 or 2. I would say I don't always round up to 5. Round up to 2.5 seconds. So, and I quite often will use an odd number one. So your ICA today, you're just going to round up by 1. You don't have to round up the nearest 5. All right. I think the book likes you to go up to 5. Okay. In practice, I quite often have like an 87-second cycle length or a 90-second cycle length. I definitely don't have a fraction in there, but I don't always round up the next 5 through there. L, you knew this from last time. What's our total lost time for this cycle in seconds? What's lost time? Right. It's the first 2 seconds of green plus 1 second of the yellow plus all of the all red time. Your X sub C is your critical volume to capacity ratio for the entire intersection. Before, we were just doing V over S, which is your volume to the saturated flow rate for your lane. V over C measures the volume to capacity ratio of the entire intersection. So that's an indicator, a very similar indicator, but it works on a global level for the entire traffic signal or signalized intersection. So the entire intersection has this one ratio, and you can either say, well, I know what my X over C is, my X sub C, is, or I know what I want it to be. Like, so a 1, you can have a volume to capacity ratio greater than 1, but that's bad. We don't like those. And so we would aim to keep a traffic signal in the 0.7 to 0.8 range. If you can help it, you don't go over 0.8. It's for that. So that could be that you pick what you want your X sub C to be for there, and not let their intersection get too close to capacity, which is 1.0. That's how that works, right? And so here's our flow ratio, and here's that individual critical lane group flow ratios. Here's the sum of V over S sub Ci, which is that big capital Y sub C we just calculated back here. That's what this guy is, right? So we would plug in 0.71 here in this equation. That's that. This X sub C, maybe our target volume to capacity ratio is 0.8. We'd put 0.8 in here, and here is the lost time we've got, which could be 3 or 4 seconds. It's quite a common one. You work all that out, and you'll get your minimum cycle length for that. Right, and so that gives you, and maybe it's 80 seconds, maybe it's 85, something like that. All right, that will give you this minimum cycle length. Well, what do we do with that now? So now we know what the cycle length is, but we don't know how much green time southbound through, southbound left are getting. Right now we have to figure that out. And so that's what this comes into. Then, so this is the effective green time, it's little g, right? Effective green time for each phase. And for that effective green time for that phase, so like phase 1, you use this V over S ratio from your critical lane in that phase number, times the cycle length that you just picked, divided by your intersection the V over C ratio that you want for that intersection, your X here. Sorry. This one's for the intersection as a whole with the C. This is your V over C ratio for that lane group that you were looking for, right? And so we went through this problem. We had the same numbers as before, right? And now they're going to tell you they want an intersection V over C of 0.9 for that, right? And so that's that would plug in here. This would be that 0.9. We'd be plugging into this, right, through there. And then we work through these problems. And so these would be the same, that same critical ones as we had before, right? So that would be calculating the minimum cycle lengths that you need based on and this V over C ratio for that lane group that you've got right through there. And the book, I know, has a couple examples in this that works through and shows you all the answers to that. It's hard to do this. Usually I do this on the board. It's kind of hard to do that on this setup through here. I'll try to find a couple examples and maybe post them for you on the Blackboard site through that. So we'd work through this. We're given what that V over C rate. They're going to use a 0.9, which I think is a little high. But in a lost time of 4 seconds, you can then plug that into this equation right through here to get your C minimum. That's 4 seconds. That's 0.9. This is this guy, 0.71, right? And then so that would give you your C minimum through that. And then you would round that number up slightly to get your ratio, right, through there. This X sub I would use probably that point. I would probably go with, I would still use the this X of C, this 0.9. I'd use that in this case too, through there. All right, so that's the C minimum, but what's the best cycle length? That's the minimum cycle length that will serve all those phases and keep people at their minimum, right, through there, or at least have that X over C that ratio there, V over C ratio that you wanted, the X sub C, the 0.9. That C minimum is just enough to make that work. It may not be the best cycle length. So then we have this other equation, which is optimal cycle length. And so that's usually bigger than your minimum through there, almost always is, all right, through there. And there's a lot of ways to try to find these, and it's not easy, right? And so this guy Webster came up with an optimal cycle length, talking about a resonant cycle that works the best. And really the way you find that is he's got an equation now, but before we had the equation, you just set your cycle length a little bit different and keep trying, and you can go through and you can see where you finally have the lowest delay through that. And so you can kind of cycle through that and test it in the field is one way to find your resonant cycle length through there. And nowadays people have developed equations that come up with that. So our optimal cycle length, different equation, right, than the minimum cycle length. Here's our optimal. We take 1.5 times the lost time plus 5. It's just plus 5. Throw it in there. And then 1 minus the sum of these critical lane groups. And again, this is going to be that 0.71 we had from before, right? And so that will find the optimal cycling. And you'll see that's usually a fair bit or a little bit higher, at least than the minimum cycle length, right, through there. And then with that, you can allocate green time from your optimal cycle length with this equation. And so you take this, the C optimum length we got from this equation, drop it in here, minus the lost time, and then you divide that by the sum of all the flow ratios, right, from all of the lane groups through there, and then you multiply it by, so this is the sum of all that's actually this guy, the sum of all those flow ratios for all the phases, and then you multiply it by the critical flow ratio for the phase you're looking at. That's what the I here is for. So this could be phase 1. The effective green time of phase 1 is the V over S, the critical V over S for phase 1, times this guy, right? And so this is a constant through all these equations, and then you cycle through for each phase. So phase 1, you multiply that times the critical lane group movement for phase 1. For phase 2, the effective green time, you take the critical lane movement for phase 2 times that for phase 3, and so forth, right? So we'd come back to this one, we would be picking these numbers, right? So for phase 1 timing, we'd take 0.21 times, we take 0.21 here, we'd plug that in for phase 1 times the optimal cycle length determined minus the lost time over the sum of all of the flow ratios for that. And again, the book has some pretty good examples that show how to go through these. And I think a couple of you said you didn't have your books with you. You weren't able to return to campus to grab them. So I'll find a couple examples and post them, and that'll help you do the in-class assignment. So the in-class, it asks you to go through and calculate these effective green times through there. I'm not going to have you do that because it gets really confusing. It would be nice if we were in class, right? That's where it'd be nice to walk around and we could talk about it as we go through. So I'm just going to have you calculate the minimum cycle length this time. So just the first piece, or actually maybe it was the optimal cycle length. Anyway, you're just calculating the cycle length, whether it was minimum or optimal, I can't remember. Through there, you're not going to calculate the effective green times. Now, it'd be good practice if you went ahead and did it, and I'll post the solution here in a couple days once the due date's passed on that one. Through there. So that's your first taste of how to time traffic signals. And again, these would be fixed time signals, and so they are not reacting to the vehicles that are there. They're not actuated signals. They don't react to when cars arrive or not. But it's always this is honestly how we start normally. This is our starting point, and then we adapt them a little bit for the adaptive. Makes a pun there. But that's not this would be our initial settings, right, through there. And then we can use the adaptive signal pieces, like reducing time because there's no one there, skipping phases because there's no one waiting at all, and so forth. Then that actually improves it from this point. This would be our starting point. The adaptive signals then can improve from there on that. Okay, well, that'll be it for today. We'll see you again for Lecture 28.